It's a pleasure to be here, and thanks in particular to David, Fernando, and Chris for putting all of this together. As the title might suggest, I work on 3D computer vision. And 3D computer vision is adjacent to, I'd say, two fields of AR, VR, and robotics, where we as a community have been made or there's this promised future that, the general audience imagines will happen at some point in K years from now, right? There's the promise of AR, VR systems where all of us will perhaps live in a future where maybe if I'm having a call with my parents, it's in a much more natural, interactive setting than this sort of boring FaceTime. We'll have our office meetings with colleagues who are far away in a much more natural, etc. On the side, there's also this promise of robotics, highlighted in this Jetsons cartoon that I was a fan of as a kid, that we'll have these general purpose robots that can help us in a lot of our mundane things, right? And towards both of these, maybe slightly different promises, there is some common paths to these, right? So for instance, when we have these AR, VR interfaces, to populate these, we require these diverse 3D assets of everyday objects and scenes that will form the elements of these AR, VR interfaces that will be created. Right? Similarly, when we are learning these general purpose robots, one of the typical ways that we do so, at least do so scalably and reliably, is to create these simulations of a lot of these systems which mimic these tasks that we want our real world robots to eventually be able to perform. Right? So we have these diverse 3D assets that will hopefully form the basis of these AR, VR systems and be used in various ways to create these realistic simulations that our robots can kind of learn from at scale in a safe manner without destroying our houses and dishes in the learning process. Okay. And I think the key question for me is, how do we acquire these diverse 3D assets that will be useful for all of these applications? I think the current paradigm for this is you hire someone to create them, right? So typically there is some designer who designs these assets, some designer who designs these simulations. In fact, I went ahead and looked at even some job listings for these. So for instance, if you want to make 150K or something, you can get hired at some of these companies. You can even design a simulation model for a single wheat grain and get paid a few $1,000s for that. So we have this huge demand of creating these diverse 3D assets that can be plugged into these simulators or real. But of course, this is a very effort-intensive process, and I'd argue it's not really scalable if you want to create many, many diverse kind of things. So the goal for me is that if we do want these 3D representations of the world that are interactive and which robots can play around with, which humans in VR can play around with, and the hope is that instead of having artists design leads, we can just have perceptual input that you as a user just walk around, capture a couple of images of your kitchen or for your scene, and that can give you these 3D representations. Alternately, maybe you can just give a text description to a generative AI system which says, okay, I want a kitchen with these assets, and it gives you this interactable 3D representation structure. And the goal is to have these neural networks which map perceptual input or perhaps these text descriptions to create these interactive 3D representations. Therefore, this is easier said than done, and there are many, many challenges. And in fact, a lot of the research in my group is focusing on resolving some of those challenges towards this goal of having these physical models of the underlying world from perhaps just perceptual input or just textual descriptions. And in particular, some of those challenges are that you want these representations to have complete 3D, right? Like my laptop is on this table. If I lift my laptop, that table continues beneath it. And if I have a system which is going around and capturing 3D, it needs to understand that there is this complete 3D representation of the world and not just the stuff that it can directly see there. Ideally, we want this process to be relatively easy for users. We don't want you to go around this room, spend 1 hour, 30 minutes and trying to lift every cup. So ideally, this should be something that you can do by just taking a video or a few images. Alternately, and this is something really, really critical for VR applications, you want these systems that don't just capture the appearance as it currently is, but you also want to imagine this room on a more sunny day. Okay? And lastly, this is again something that is perhaps important if you want a human to be able to interact with these scenes or a robot to be able to simulate these scenes, is that it should understand not just how the world currently is, but how it can change, that drawers can open, that coffee can spill, and all of this will be critical for, let's say, robots that don't deliver from these systems. And so today I'll maybe give you a slight dive into some of these problems that we've been looking at, in particular relating to acquiring spatial 3D representations of the world from. So focusing on reconstructing and generating 3D, I want to just give you a brief glimpse of some of the research ongoing in our group, where we try to capture 3D representations from just a handful of images. So imagine just an eBay product listing of some object, and given just the small number of images, we want detailed and accurate 3D representations. We want these representations to be relightable. We want to be able to view them in arbitrary new environments and appear realistic. And perhaps we also want to enable this 3D generation from not even perceptual input, but just sort of creative captions that a user can give, and we want systems that can generate high fidelity, realistic 3D representations from just descriptions. And so in context of recovering 3D from maybe images, the typical pipeline, if you have looked at recent 3D reconstruction methods, is as follows. You take many images of an object that you're interested in reconstructing, you run an off-the-shelf pose estimation system which says, hey, given these 10 images, this image is from here, this image is from here, and so on. And then you optimize your favorite noodle representation or Gaussian flattening representation, which gives you a nice 3D monologue scene. Okay? The issue in our application is that even this first step, which tries to estimate poses of images given many views, it works really well if you have hundreds of images of the object or the scene that you're interested in. But as soon as you say, okay, here are 10 images of this object, give me poses, just catastrophic it fits. So sort of the first challenge in having this system that can, from casual sparse captures, give you 3D, is just to understand where the images were taken from. And sort of classical solutions are unfortunately not at all applicable or robust in these scenarios. So this is something we've been looking at for maybe 3-4 years. And perhaps the most recent one idea that I think is really interesting is that normally when I say I want to find cameras, if I ask anyone, how do you port cameras? The typical answer is that, oh, camera is a rotation matrix and a location of the camera and perhaps a matrix. Instead, what we have been pursuing is that instead of thinking of cameras as these global matrices, we can say, oh, camera is a mapping from pixels to rays in the world. If I have a camera here, then this pixel corresponds to this ray. If I have a camera here, then this pixel corresponds to this ray. And you can parameterize camera as this ray image. And it turns out neural networks are really, really good at predicting images from images. Like the typical transformer architectures that we have are really suitable for saying, oh, I have a lot of patches as input, predict something for each patch. And so this representation, which we sort of show is that analogous to the classical camera representation that you may have thought about, is much more friendly for neural networks that try to predict this. And so we can train maybe denoising diffusion neural networks which predict these rays given many images. So here's just a fun visualization of this neural network trying to iteratively improve its prediction of these rays, sees all these images, for each image it tries to predict the ray for each pixel, and at the end of the day it just recovers cameras for those. And it works remarkably well given just a small number of images. The black cameras are the ground truth. Our inferred cameras are really, really close to this, can handle symmetric objects and so on. Okay. So we needed to rethink a bit about how do we estimate cameras. And more recently, we've also been extending this camera estimation to also geometry estimation. So for instance, you can say I'm predicting rays. Let me also just predict where each ray ends. And that gives you a geometry of the scene, because for each pixel, you're not only predicting what its ray in the world frame is, but also what 3D point is that particular ray seeing. And that gives you basically this classical structure from motion points and camera representation, but in a much more sort of learning-driven manner. And we've been sort of trying to, and works better than some other systems, and we've been trying to make this more robust in other scenarios as well, not just the objects, but let's say these aerial and ground images. So I think this is Wien Hall at CMU. I'm not sure if you've walked through it, but current systems just don't understand how to register these aerial and ground images, and we've been training them to sort of better understand this. Like given just these two images, our system can tell you, okay, this particular image is taken from here, this one is taken from the ground, here's the geometry that you see. Okay. So we've made a bit of progress in being able to register these cameras. And so systems like ours, unlike classical systems, can now give you, given a small number of images, can give you pretty accurate cameras. But turns out that's not the only issue. We can just say, okay, I have now cameras that I trust. Let me reconstruct a scene. You still don't get very good results. And the issue is that if you're just seeing an object or a scene from a handful of viewpoints, there are just not enough constraints to reconstruct a nice scene. There are still unobserved aspects. Each 3D point maybe you've only viewed from one image, and multi-view geometry just fails if you only have sort of a single view observation for each 3D pointers. And so the key idea in our group has been to also incorporate generative priors in some way. So generative priors about the world, no images look like this, objects generally look like this. And that is a very strong constraint of, hey, I'm trying to reconstruct a 3D object, I'm trying to reconstruct a scene. the representation better make a generative prior happy that, renderings of this object should match my intuition of what images generally are. And adding that in some way really improves the reconstruction quality that we get. And so the previous example improves significantly, and given just 8 images of this generic object, we can give you a very precise, detailed reconstruction. And just a couple more examples. I think the left one is a toy that one of my collaborators' kid was playing with. So just 8 images of that toy and you get a pretty good reconstruction. Just a random can that you can find around your house, you can get about a detailed reconstruction from just a few bullets. And this idea that generative priors can help improve 3D estimate is not just restricted to improving the geometry, etc. And this is actually work with Fernando, where we can also learn generative priors for what the underlying materials should. So this can help us understand some priors about what the roughness, albedo, or some material properties of all of these objects can be, and that can give us much better relightable representations, because through some data we have learned priors on what these decompositions like albedo, roughness, metallicness, etc. can. And so I've been talking a bit about the use of generative priors for guiding these reconstruction. Lastly, we've also been looking at learning these generative priors or learning these generative models that can directly give you 3D outputs from something as simple as a text description. And perhaps we've all seen this example of success of generative modeling for images, where we know that state-of-the-art generative models can give you really impressive high-fidelity generations given an arbitrary text prompt like this avocado chip. The issue for learning similar generative models for 3D, where you're saying, okay, I'll have a text, I just want a 3D representation, is unfortunately just data. The kind of data that we have for training 3D models is unfortunately just not diverse. So the main insight that we have had is, instead of learning generative model priors for 3D representations, let's learn generative priors for multi-view generation, that given a text description, you'll generate, let's say, 8 images of an object. And here we can use existing image generation models and tweak them slightly so that they can generate many images. And then just say, okay, let's deterministically reconstruct the 3D representation. And in fact, this procedure not only gives us good generations, it gives us like ultra fast generations. Like in the third of a second, we have models that can go from a text description to a nice 3D representation. And here are just some sample results on different complex prompts. So for instance, you can kind of imagine some dog wearing graduation regalia, or you can be more creative, a line reading newspaper, etc. It's really good at generating these compositional prompts, and works actually remarkably well, and just does so in maybe the third of a second. So yeah, I think that's all I wanted to talk about, and yeah, I'm happy to chat with anyone here or later offline. Keep me to reach out if any of this seems interesting to what you might be asked before.